Alright, so continuing for today. Sorry I couldn't get everything in class. That's my bad. But as long as I got my notes out here, I might as well take a minute here to read some quotes from the start of the chapter. Cauchy wrongly asserted in 1821 that infinite series of continuous functions was once more continuous. And then in 1826, Abel provided a counterexample. And Abel had this to say: if one examines more closely the reasoning of which is usually employed in the treatment of infinite series, he will find that by and large it is unsatisfactory, and that the number of propositions about infinite series which can be regarded as rigorously confirmed is small indeed. Alright, so in other words, the things we're wrestling with in class right now, they threw the best mathematicians of the early 19th century for a loop. And it took us a long while, actually, to really understand what was going on here and to unravel it. It was, in fact, the introduction of that uniform convergence we defined today that was in large part responsible for sorting these issues out. That notion of uniform convergence is apparently due to the teacher of Wirestrauss, Christopher Guderman, wrote in 1838. It is, in fact, worth noting that the series just found all have the same convergence rate, quote-unquote. So Weierstrass used the concept of uniform convergence throughout his work, and I guess also of note, Seidel and Stokes independently in 1848 and 1847 also used something akin to uniform convergence of series, but as the eminent British mathematician G.H. Hardy said, the credit goes to Weierstrass, because Weierstrass' discovery was the earliest, and he alone fully realized its far-reaching importance as one of the fundamental ideas of analysis. Cauchy eventually came to the right side of things in 1853. He kind of in the midst of a work that used and made significant contributions to the theory of uniform convergence series, he wrote that it is easy to see how one could modify the statement of the theorem. I don't know, I'm not quite giving justice to the Cauchy thing here. You can read, this is a reference to Reinhold Remyert's excellent masterwork on complex analysis, which I have taken quotes from because he's got lots of nice history in there. So my notes, Guide to Gamelin, it's Gamelin, yes, but also I have read Remyer's complex analysis and taken some choice quotes from here and there. All right, so I said we were skipping 5.1 in lecture. I guess that's true, but anyway, I should talk a bit about some of the stuff in 5.1. This is just the definition of series, which is the limit of the sequence of partial sums, same as in Calc 2. And you know, the sum of the series is you can add series, you can multiply series by a scalar. Right, nothing new there. If the real and imaginary part of the series, those converge if and only if the linear x plus I, the complex linear combination of the series likewise converges. All right, great, whatever. Excuse me. And then here we have a result about comparison of series, which is, fine. Here's the nth term test, which in this case is the jth term test. If the series converges, then a sub j goes to 0 as j goes to infinity. All right, we'll use that. And then here's another one that's important. So if we have the sum j equals 0 to infinity of z to the n, all right, which let me just write that out in. Let me zoom in here a bit. Sorry, Lego Donald Trump. There you go. Here I have the picture. Let's see here. So this would be, in other words, 1. Can you see me? Yeah, I can see. 1 plus z squared plus z cubed plus dot 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 dot. Right? That converges to 1 over 1 minus z. For the modulus of z being less than 1. Okay, so this is the geometric series. It still holds for complex variable, all right? And so that is proved by direct computation on the next page here. So do the same thing as I do in Calc 2. We look at the nth partial sum, z times the nth partial sum, subtract them, and that gives you this formula. And then as n goes to infinity, this goes to 1 over 1 minus z, provided that the modulus of z is less than 1. All right. We also define absolute convergence for complex series, just as you'd think. The series says to converge up absolutely if the series of the moduli converges. All right, and we have comparison sort of test that if the series is absolutely convergent, then excuse me. Let's see here. Trying to decide whether or not this theory is... Yeah, okay, so here, if you have a complex series is absolutely convergent, then it converges. And also the modulus of the sum of the series is less than or equal to the sum of the moduli for said series. All right, so... And I include in the notes a proof of the absolute convergence theorem for real series. You can look at that if you want. Anyway, so that's pretty much it from 5.1. There's 5.1 in 6 minutes. I hope you don't mind. I needed to remind you that we had that the geometric series converges to 1 over 1 minus c, because that's actually used in the examples in 5.2 or 3 that I want to talk about. So, all right, so from class today, in class we already talked about this part. We talked about this and this and this. And what did we get to? We got all the way over to definition of uniform convergence. And then we had theorem 5.28. I took too long to prove that today. Thanks to Audric for setting me straight. Let's see here. Where did we get to? We did that. And we proved this theorem 5.29 that, we proved that one here. Let's see here. And then finally, here it is. Definition of a series, right there, of functions. So here it is. Let's see here, where am I? I'm trying to find out the how far my frame goes. I need to build a better setup here. All right, so definition 510, if you have a what? That seems wrong. Sequence of complex valued functions, the partial sums are this series. I think, well, there's a couple different ways to fix the initial sentence. Let me say this. If I just cross out the sum, maybe that makes it make sense, all right? So let's cross that out. Let fj be a sequence of complex valued functions on E. The partial sums are functions defined by Sn of z. Sum j equals 0 to n of fj, all right? Great. The series, sum j equals 0 to infinity, fj, converges pointwise on E if and only if the corresponding sequence of partial sums converges pointwise on E, okay? And the series converges uniformly on E if and only if the series of if the sequence of partial sums converges uniformly on E. Okay, there we go. I think that fixes it. The other possible fix here would be to replace the word sequence with series in the first sentence, but I think I like this more. Okay. So the Wirestrauss M test is our fundamental tool for judging the convergence or lack thereof of a series of complex valued functions, okay? So the Wirestrauss M test says this. Suppose you have mk's a non-negative quantity, then and that the series with terms m sub k converges, all right? If gk are complex valued functions such that the modulus of the gk's of z is less than mk for all z and e, then we say that the series formed by gk converges uniformly on E. I mean, this is not a definition, this is a result, okay? And so here's how that goes. So what you do is you assume that you've got this mk, which is larger term by term than gk on mz, right? Then by the comparison test, which was in section 5.1, we have absolute convergence of the series gk of z, right? And so that means that it's convergent, right? And we're going to call the function to which it converges g of z. So in other words, the sum of the series of the gkz is g of z. And more than that, we have the estimate that the absolute value of g of z is less than or equal to the series of the moduli, which by assumption is less than or equal to the series of the mk's. All right? So therefore, the difference between the sum of the series, which we call g of z, and the nth partial sum of the series is given by this, all right? And more than that, this is bounded by the corresponding tail of the what's called majorizing series. So M is sometimes for majorant. Okay, so, but we assume that this is a convergent series, right? So the tail of any convergent series has to go to 0, which shows you that has to go to 0, which is, in other words, to say that you have a worst case estimator for, so you have a worst case estimator for the nth partial sum of g of z minus the sum of the series g of z, given by the tail of the majorizing series, which then again goes to 0 as n goes to infinity. So therefore, the series formed by gk converges uniformly on E. Oh, well, that's nice. So definition, a series of functions, right, is dominated by mj if the modulus of fj of z is less than or equal to mj for all z on E, right? I'm missing my for all z of E in here. That's kind of important, right? Oopsie. For all z in E. That matters. You got to have that, right? And when the sum of mj converges, we see that we will call the mj a majorant for the series fj, all right? So just to reiterate, if we can find a majorant for a given series of function, it will serve to show that the series is uniformly convergent by the Wirestrauss M test. Fun historical aside, Wirestrauss gave this M test as a footnote, kind of an afterthought in a paper he wrote, or a book he wrote in 1880. Der Funktionenlehren, I can't say it. See, anyway, page 103 of Reinhold Rumeert's awesome book. Anyway, so, okay, I hope maybe I'm convincing you of nothing else. A second book to read in complex analysis, that book by Reinhold Rumeert is really, really, really top notch. It's a great source of history and deeper thinking in complex. But okay, so just to go back to that geometric series again, the geometric series converges, right, to that's its sum, as long as the modulus of z is less than 1, right? And we also calculated explicitly that so this is the series, the sum of the series, which is so this is 1 over 1 minus z, minus the nth partial sum of the geometric series. That is actually equal to the modulus of z to the n plus 1 over 1 minus z, right? And so that's your worst case estimator, essentially. But the supremum thing is, it shows you how to calculate the worst case estimator, right? So the supremum of this on the unit disk is unbounded because, see, you can get z arbitrarily close to, modulus of z equal to 1 here, so that makes the denominator get arbitrarily close to 0, which makes this thing blow up. All right, so this series does not uniformly converge on the entire unit disk. All right. However, if we just instead of trying for the whole unit disk, right? If instead of trying for so like suppose this is the whole unit disk, right? Here's E. All right. So we can't do the whole unit disk. We don't get uniform convergence on the whole unit disk. However, all you have to do is just look at instead any radius r disk inside there, right? And once you do that, on such a disk like this, we can't we still have this calculation holding, right? But then the denominator can't get to 0 because you only have modulus of z. This is for r less than 1. You only have the modulus of z getting at most just approaching r, not even quite getting there. Well, okay, if you excuse me, include so this is the open disk, right? So you don't even quite get to modulus of z equal to r. All right, and so in that context, you can use the majorant series, just r to the power k, because this is a geometric series. If r is less than 1, it converges to 1 over 1 minus r. That's a majorizing series for the complex geometric series. And that shows you that the complex geometric series is uniformly convergent on any disk of radius r by the Wirestrauss M test. All right. So, in other words, this is pointwise convergent, but not uniformly convergent on the entire unit disk D. All right. Let's see here. What else can we say? If we look at, so another example. Hey, come on, paper. Work with me. I got to go to baseball practice here pretty soon, so. Another nice example is z to the k over k cubed, k equals 1 to infinity. So here you can use the p equals 3 series as its majorizing series, because as long as we've got modulus of z less than 1, the modulus of z to the k over k cubed is less than 1 over k cubed. And that, if you add those up from 1 to infinity, converges. It's p equals 3 series, right? So therefore, by the Wirestrauss M test, we find that this series converges uniformly on the unit on E, right? So not everything is like the geometric series. There are series which uniformly converge on the unit disk. It's just that not the geometric series, okay? All right, so now let's see how we saw earlier today that we lose continuity sometimes, we lose differentiability other times. What's the deal with so what's the deal here with, come on, behave. Sorry guys. What is the deal with holomorphic functions and their sequences or series, right? So here's an important theorem. If you have a sequence of holomorphic functions, all right, on a domain D that converge uniformly to f on D, then f is holomorphic on D. Hey, that's pretty nice. So let's see how that goes. So we're going to use Morera's theorem. Notice that we proved before that holomorphic on a domain implies that the derivatives are continuous, right? And let's see here, I guess we don't need that actually, but fj holomorphic implies fj converges to f. Let's see here, why is that? Which is continuous on D by the supposed uniform convergence and theorem 5.2.8. Let's see here, it's been just long enough for me to forget theorem 5.2.8. Let's go back here just a second. It was like hours ago that we covered that. That is this one. Theorem 5.2.8 is a sequence of complex valued functions if each one is continuous on E and if fj converges uniformly, then the limit function is also continuous on E. Okay, right. So we've got a sequence of holomorphic functions that, so if it's holomorphic, that means it's complex differentiable, so each one is continuous. And it's assumed to be uniformly convergent, so okay, yes, then its limit function exists and is continuous by the theorem 5.28, right? So what does it remain to show? It remains to show that that limit function is holomorphic on D. How do we show something's holomorphic on a domain? Well, we could use Morera's theorem, right? And to do that, we look at a rectangle with sides parallel to the coordinate axes. And remember, theorem 5.29 said what? It said that we can, for a uniformly convergent sequence of functions, we can exchange the order of integration and the limit of the sequence, right? That was this one. And so, all right, so we've got the integral, as j goes to infinity, of the integral around the rectangle fj z of dz. So we exchange the order of the limit and the integral using the uniform convergence that we're assuming, right? And then, but remember, we assume that this function converges to f of z, right? And so we have this equality. But we also have that each one of these is 0, because remember, we're assuming that that's a sequence of holomorphic functions, right? So holomorphic means that this integral is 0 by Cauchy's theorem. So we have the limit as j goes to infinity of 0 is equal to this, which then shows us that the integral of the limit function around an arbitrary rectangle with parallel sides to the coordinate axis is 0, which by Majorizing's theorem proves that f of z, the limit function, is likewise holomorphic. So that's that theorem. All right, so there's the rest of the theorem. Now, next up here, we've got theorem 5.2.16, which is a little bit more technical. If we have a holomorphic sequence for the disk of radius r, and suppose you have that the sequence converges uniformly to f in that disk, all right, then for each r less than the big R, and for each m greater than or equal to 1, the sequence of mth derivatives converges uniformly to the mth derivative of the limit function on that subdisk, all right? So the proof is by Cauchy's generalized integral formula. And there's a typo here, unfortunately, in my notes. See, this right here, I'm doing an integration over w. That really, I believe, should be a w, right? So basically this should go up there as well. That shouldn't be a z, that should be a w. That would make more sense of this formula. All right, so anyway, excuse me. The convergence of fj is uniform, we're assuming that. So we can select the worst case estimator, right, that bounds the difference between the limit function and the sequence, the j function in the sequence, right? And that's going to hold for z less than r. And of course here the epsilon j goes to 0 as j goes to infinity. So I say fix an s that's between little r and big R, all right? So here's a picture. So if I can get my picture on here. The big R is outside, the little r is inside, and this s is somewhere in between there. All right, between the little r and the big R. All right. We're going to apply Cauchy's integral formula to the mth derivative of the difference of the jth sequence function in f of z on this disk of radius s. All right. So really, on the not the disk, we're not really applying Cauchy's integral theorem on the disk as much as we are applying Cauchy's integral theorem on the circle of radius s centered at z0. And so Cauchy's integral theorem, well, first of all, the mth derivative of this is exactly the difference of the mth derivatives of the jth sequence function and the mth derivative of the limit function. All right. Excuse me. And of course, that's m factorial over 2 pi I, integral around the circle, radius s of fj of w minus f of w divided by w minus z to the m plus 1. All right. And let's see here. This is assuming that z is somewhere inside the disk of radius s. So you can kind of almost see it in my picture down here. Z is in there somewhere. All right. Okay. And so notice then that the modulus of w minus z, you can add and subtract z naught, and then by the sometimes use triangle inequality for getting denominators to behave. This is greater than or equal to the absolute value of the difference of the modulus of w minus z naught and z minus z naught, but remember w minus z naught is straight up equal to s on the integration we're looking at. and z minus z naught is assumed to be less than or equal to r. So certainly if we subtract r, that's worst. That's the worst. That's the smallest you can make this, right? So if this is biggest that can be is r, then we take s minus something. The make that quantity largest, we should subtract r from that. And okay, so s minus. So there's the least that this could be is s minus r, which when we divide makes this the biggest. All right, so for w minus z is greater than or equal to s minus r, so we get this estimate here. All right, and since the let me scooch down here a bit. Since the so notice there's a typo right here. Certainly this I should not be in the estimate. If this is the modulus, this should be a real number. So just a cut and paste mistake that I is not there, right? When you when you make this calculation, you don't get the I there, obviously. But otherwise, looking at the the ML theorem on Cauchy's integral formula here gives you that the modulus of this is how to say this? Okay, so this is an estimate right here, if I'm not in frame or not. This right here is a bound for the integral, the integrand up here, right? So ML theorem says that the modulus of that, which would be, sorry if I'm out of frame again, aren't I? I can't see where I am. So the modulus of this is equal to the modulus of that, right? But the modulus of all of this is less than or equal to the bound on this integrand times the length of the curve which you're integrating, right? And then of course this rides along. So I should have an m factorial over 2 pi out front down here, so I'm trying to say. So sorry if I'm jumping around a bit. So that is m factorial over 2 pi, the I is not there. And this is a bound for the integrand, epsilon j divided by s minus r to the n plus 1. The length of the circle is 2 pi s, and we call all of this rho j. And then the thing is, you can argue that since m is fixed here, this rho j goes to 0 as j goes to infinity, which serves to show that it's serving as a worst case estimator for the series of mth derivatives. In other words, the mth derivative series is itself uniformly convergent, right? So I shouldn't say the series, but the sequence of mth derivatives is uniformly convergent by this calculation. So that's, just to reiterate, we have the result that a holomorphic sequence of functions which converges uniformly, right, necessarily has not only the derivative of the limit function existing, but in fact the mth derivative of it converges uniformly. That is so much nicer than what we saw in the real case. Now this brings us to define and so, again, Gamelin keeps using the word analytic. We will soon use the word analytic with meaning, but that time is not yet. It's soon though, maybe Wednesday. So a sequence fj of holomorphic functions on a domain D converges normally to a holomorphic function f on D if it converges uniformly to f on each closed disk in D. So this is the behavior we saw for the geometric series, all right? And so here's another thing we can say from all this. If we have a sequence of holomorphic functions on a domain that converges normally on D to a holomorphic function f, then for each m greater than or equal to 1, the sequence of mth derivatives converges normally to the mth derivative of the limit function on D. And this terminology, normally convergent, it stems from a rather famous mathematician by the name of Baire. He had a theorem called Baire's category theorem, which you might see in, for example, the study of topology. And anyway, here I think this quote is worth kind of digesting. So just to put things all together, the Wirestrauss M test actually provides normal convergence. And In summary, local uniform convergence is a natural mode for sequences of holomorphic functions, whereas normal convergence is the preferred mode of convergence for series of holomorphic functions. Remember in the real case, if we have functions, if we have like just convergence of series, then there's something called Riemann's rearrangement lemma, which means you could have a conditionally convergent series, and conditionally convergent series can be rearranged to give different sums. Something similar happens here with series of functions which are just uniformly convergent. In contrast, if we have normal convergence, then we can rearrange the series of such functions and not change the outcome. Okay. And anyway, this is a fun quote from Baer, who introduced the term normally convergent in 1908. Basically, he's apologizing for the introduction of the phrase, but he points out that he found that this concept of normal convergence makes everything easier, essentially. That brings us to section 5.3. All right. So section 5.3 is on power series. All right. And I suppose we'll start there next class. I should probably do these things in class. Sorry to go over time today. My bad.